darker.
Do you know where to buy the pencil lead?
Pencil lead. Eason's has everything.
No, it's not have 0.5.
It does.
No, it only has 0.7.
I went there. They
But
had.
last time I asked them for 0.5.
Maybe they didn't understand what you were talking about.
Yes.
They're disgraceful. Disgraceful.
You got it.
Which Eason's?
Got it.
O'Connell Street?
In the next to the penny.
Yeah, O'Connell Street. They should be good. Who did you ask? Young or old person?
The person in
The only good thing about it is the cashier.
where I money.
Cashier.
Maybe you should ask someone on the floor.
Yeah, we should have done
Yeah.
it.
Yeah, I also asked, and she said go to the
Really?
the cash money.
Oh, okay. Strange. Strange. Oh well. That's life. Okay. Kinetic model of a gas.
Brownian motion.
Hey, you're smart. Yes. You got this? Yeah. Yes, 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 yes. Yeah?
Oh,
Yeah.
oh,
What?
this is our last lesson of the day.
Yeah, so? It's not my last lesson.
Yes, I know. Nine.
Definition. Pressure is a word you probably know. What are you doing? Pressure means how much something is pushing on something else. So as a formula, pressure is force over area. Huh?
How much something push
What's the exam? Don't push me.
or pull or put
No, pressure is force on area. Yeah, force over area is pressure. So what's the unit for pressure?
Newtons per meter.
Yes, square.
Meter squared.
That's the one. Newtons.
Pascal.
Yes, yes. Pressure, P. F force and A area. The units are pascals, which is just the same thing as a Newton per meter squared. So 1 Pascal is just a Newton of force on 1 meter squared.
it's P
PA for Pascal, the unit,
and the pressure
is P.
area.
Huh?
An area. Area.
Yes. Is it a or an area?
And
It depends on how you pronounce it. A area, an area.
An area.
no, it has to be an and because area starts with a vowel.
Yeah.
Rules 101.
No, yes, I'm aware of this, but we don't always use that if the vowel is not pronounced quite like a vowel sound. For example, say the word H-O-U-R. What's that word?
Oh.
So put,
Yeah.
what would you say in front of it?
An hour.
An hour.
Yeah.
But it doesn't start with a vowel, it starts with a vowel sound.
But area does sound maybe.
Yeah, so when I was saying it and typing it, I didn't quite get the vowel sound. So that's why I typed it as a area. But if you pronounce it more correctly, then you can say an area. Okay?
In English, what do we use?
But it depends. The A and an is on the pronunciation, not on the spelling. So perhaps in one country they pronounce it in such a way that it's a area, and in another country it could be an area or whatever. So it's not like it's this and it has to be this.
What's the unit of pressure?
Pascal, PA.
Yeah.
No.
Yes. Continue now. Do you have this? Yes? Okay. It's the same as 1 Newton per meter squared. Yeah? Okay. Right. So, we shall consider our ideal gas to be as shown. Note we shall assume... Okay. So, I don't know if you've done this in chemistry. Ideal gas, is that something you studied in chemistry?
Yeah.
We have a
Ideal gas, temperature
Yeah.
and pressure.
You did that in chemistry this
I
year.
just took the values.
Yeah.
Yeah. But you've heard the term ideal gas. What is an ideal gas then?
A gas that behaves like a gas in room temperature.
Yes.
No, a gas that is at
No,
room
good enough.
temperature and pressure.
You can change that pressure.
A gas that other gases want to be like?
Kinda.
Oh, those ideal gases think they're so great. Ideal gas, does anyone actually have the definition of ideal gas? No.
The gas that's
No, you don't. Nobody does. So ideal gas is a regular gas with some extra properties that make it nice to work with mathematically. So it's just a gas, but it's a gas that has certain properties. Like for example, low density is one property. Let's actually have a look at the properties. So I said low density is one, but let's see what I actually wrote down. So the first one, low density. That's what you need for an ideal gas. A low density of colliding particles. So the gas is just, as you know, molecules that collide. But importantly, that the molecules don't attract. So the molecules just bounce around. They're not like pulled towards each other. So we say there's no attraction or repulsion. They're just colliding. So there's no pulling force or pushing force between them. You understand? And 4, we ignore gravity because the mass is quite small and it doesn't really affect the particle. So we don't really imagine gravity on the particle. The particle is free to move around the room as it likes. Do you understand that we won't really imagine the gravity? Of course there is gravity that pulls the gas down, but it will still happily move around up to the top of the room. It's not like the air at the top of the room is gone because it all sank to the ground, right? Yeah. So that is balls. That's right. Small balls bouncing around in a box is how we imagine it.
Not a bag?
In the picture, it's a box.
Oh.
Not a bag. With no gravity, basically. Oh, you're so dirty, Faisal.
So,
Right.
because you said it so enthusiastically.
Yes.
That is balls.
Small balls on the ground.
You don't know what we're talking about, do you? So that's a good thing. That's a good thing. Right, so let's have a look at what formula we can make for this. So I'm going to do a proof. Oh yeah, before continuing, 2 things. In the exam, they sometimes ask for those properties, so you will need those for the exam. By the way, the question is typically something like list 3 or list 4 properties of ideal gas. And wait. After that, we're going to do a proof. Now the full proof is not on the exam. However, you still need to know the proof because there has been or could be questions that test your understanding of the proof. So a question might be like, in the proof of blah blah blah, what is the first assumption, or what is the consequence of, or in other words, they'll test that you at least understand the steps in the proof. Maybe not that you remember every step, or that you could even do it, but at least that you understood it. Okay, so please write down these 4 properties, and then we'll begin the proof, which is quite long. Got those 4? Great. Lee, you wrote down those 4?
Wait.
Your physics book looks a little bigger than your maths book. Yes, there's more pages used than that. Yes?
Colliding particles?
Yes.
How's that property?
Yeah, because there's no rule that says that particles have to collide in the gas. Maybe they stick together. We don't always have collisions. They might clump together and stick and become some kind of ball, or I don't know. I don't know because we don't actually look at non-ideal gases. We only look at ideal gases in physics and chemistry. So I don't know what weird stuff happens in non-ideal gases. I take it that you didn't go into this level of detail for ideal gases in chemistry. So what was your definition of ideal gas, did you say, in chemistry?
No definition, just a value for it.
No, we didn't.
But you keep saying value like ideal gas as a number. What do you mean?
No, we
The,
didn't do anything about ideal gases.
I think we
But
were
this guy said
There's
that-
ideal gas law constant, I know.
No.
But the first time you used the word ideal gas.
What we did was
Yeah.
gases in ideal conditions. That's what we did.
Yes.
Gases in
Very
ideal
different.
conditions. That is different to an ideal gas, funny enough. Gases in ideal conditions. English. Oh, so funny. Right, can I start the proof?
Yeah.
Yep, okay.
Do we need to write it as well?
Oh, definitely, because you need to understand the proof, because your understanding will be tested. So, we said the ideal gas is a collection of particles in a box. So, I'll start off by just drawing a box, and we'll keep it simple by keeping all the sides of length L. They're all length L. So, you have your particles, and they're bouncing around inside. You understand? So what we'll do, to make it easy to begin with, we'll just look at the particle colliding with the wall in, horizontally. So we'll just imagine the particle starts here and goes across, collides with this wall, comes back, collides with this wall, and so on. I know it's not going to be, they're not all going to do this because they're moving around like this, but just to make it easy, we'll picture it like this. Okay? So we'll say that the particle moves in with speed u, and then it will hit the wall. So when it comes back from the wall, its speed or its velocity is
U.
minus u. Its velocity. Its
Oh,
speed is
that's
u,
good.
but its velocity is minus u. Let's calculate the momentum. So the momentum is momentum afterwards. mv minus mu. What's the momentum afterwards, the v? Minus u. And the before?
U.
Yeah, just u then. So this is minus 2 mu. I don't really care too much about the minus because it's just if it's a left or a right. So because I don't care about the minus, I'll just write 2 mu. Because of course if I drew the picture going this way, it'll be a plus.
Wait.
What?
This means that the atoms keep on increasing in their momentum.
No. They keep changing the momentum, but that doesn't mean increasing.
But 2 mu. So it was mu, now it's 2 mu. Correct?
No. The change in momentum was 2 mu. Its momentum is still mu. The momentum. What's the momentum here?
Where's the
Here. What's the momentum?
mu?
And what's it here?
Mu.
Has it changed?
No, it hasn't.
Well, it has because the direction has changed, but the magnitude has not.
Yes.
So it does not increase in magnitude of momentum, but the momentum does change. It changes direction.
Okay, so if it's only changing the direction, where does the 2 come from?
Because you have
Two of them.
two of them. If it was going forward with 1 unit of momentum, and now it's going backwards with 1 unit of momentum, the magnitude has not changed, but it's gone from a +1 to a -1, which is 2. Yeah? Peace out?
Yeah.
Okay. Can I continue? Great. So, that is the momentum.
Let me see how we can hit from outside of the clock.
It's been a long, stressful week, and I can see that Friday is going to be no different than any other day.
Of course not.
Right, so delta P over delta T is 2mu over delta T. I divide both sides by delta T. Why did I do that? Well, what is delta P over delta T?
F.
F. So now we have F equals 2mu over time. I'll just write T for time.
F is
Well, okay, I'll put delta T.
force.
Force, yeah.
Force of what?
Force is a formula from
Yeah, but this force is force of what?
The force exerted on the particle by the wall.
Okay.
Or, from the point of view of the wall, the force the particle exerts on the wall. The minus is the force the wall exerts on the particle, but if you're looking at the wall, then the Newton's law says there's an opposite reaction, which would be a positive. This is actually what I really care about in this proof.
So that comes from F equals ma, right?
No, we did Newton's second law. F is delta P over delta T.
Okay.
So does this
Didn't we? We did.
Yes, we did.
Yeah.
Does this mean that a gas will always try to expand its surrounding?
It's always exerting a force on the wall, so yes, I guess so. Okay, continuing. So, we have F equals that. But recently we had a formula that says pressure equals F over A. So what would F equal from this formula?
There is no A.
No, don't worry about that.
2mu over...
No, dude. Pressure equals F over A.
Yeah.
Yes.
It's above.
P.
PA. Yeah. So now you have pressure times area equals 2mu over delta T. And if you're wondering what the area is, it's the wall. So that's L squared. Yeah. So we're looking at the pressure over this area. It'll be quite small when you're only looking at one particle, of course. Now, what is area? Well, that is L squared. And we don't really like the delta T here. It's a bit stupid. We need to change it. So we have the formula distance, speed, time. So what does time equal? Distance over speed. The speed is clearly u. There's no doubt about that. Even if it's a plus or a minus, its speed is still u. But what's the distance? And this is where you have to be careful. The distance the particle travels.
It's the length.
It
Times
seems
two.
like it should be. Yeah, what is it?
Times 2.
Very good, 2L. Because the particle in one sort of oscillation of activity travels the full length twice to get back to the beginning. So we're kind of looking at it in a sort of yeah, although it's not simple harmonic motion, that's how we're looking at it as sort of a cycle like this. So that's nice, because what happens here with the 2's?
Cancel out.
They cancel out, and the u can come up the top to make a u squared.
Wow.
So I can bring the L up here and get PL cubed equals mu squared over 2.
no two.
We cancel the 2's.
That is absolutely right. So I get PL cubed equals mu squared. But what is L cubed?
Volume.
So I get P times V equals mu squared.
Okay.
Now, we have to fix the fact that the particle...
PV? No, that's not.
Okay, myself, okay. Calm yourself down, Faisal, calm down. That's it. Now, this is not realistic because the particle is going like this. But it's not really doing that. What is it? It's moving around like this. So we have to deal with that. This is how we deal with it. Imagine I was in 2 dimensions.
Wow.
And I had a particle moving left and right with a speed u.
Yes.
If I now extend this fully into 2 dimensions, not just 1 dimension, it could be moving around like this. Obviously, well, not like that, but you get what I mean, with speed u. So, it has a component. It has an x and it has a y. How much? Well, that depends on which direction it's pointing. And the direction is random. But on average, this component would be u cos 45 and this one would be u sine 45. On average. Sometimes it will be lower, sometimes it will be higher. Sometimes it'll be backwards, but we don't care about the sign right now. In other words, if you have a particle moving in 2 dimensions with speed u, we can imagine that as one particle in 1 dimension with speed of u over root 2. And the logic continues when you have 3 dimensions and it's moving around with a speed of u. Then if you look at just the horizontal component, it will be on average u over root 3 for 3 dimensions. It's like you're using Pythagoras in 3 dimensions. This gets very complicated. You can just take it as a fact if you want. If something is moving around with a speed of u on average, then in one direction its speed will be u over root 3 if you're in 3 dimensions. But if you're on 2 dimensions, it's moving around with speed u, then on average one direction is u over root 2. So in 4 dimensions it would be u over root 4.
What is 4 dimensions?
No, that's not important, I'm just generalizing. So if I want to fix this, it's not really u. That was supposed to be u over root 3 dimensions. So I need to fix that up now, and I get, continuing over here, PV equals mu over 3. Why not root 3? Well, it's squared. Oh, sorry, u squared.
But remove the square because you remove the root of 3.
It was root 3 squared, so it's 3.
Isn't it?
It was this, u over root 3 squared. That I've changed the u to u over root 3.
Okay.
So that's mu squared over 3,
Yes.
which is 2 times 2 over 3 times a half mu squared.
Yes, the two's cancel out.
2's cancels.
Okay.
Now that is the energy for just one particle. If we have n particles,
Times one.
just times it by n. We only looked at one, so no big deal, we just times it by n. But what is a half mu squared multiplied by n? Kinetic energy. And if we multiply by n, it's the total kinetic energy. Total kinetic energy. However, does this particle have potential energy? Does it have MGH? No.
because it's always moving.
No gravity.
No. Why not?
We assume it's...
We assumed no gravity. Remember one of the assumptions. So the potential energy is 0. But potential energy is 0. So the total energy is just the kinetic energy. Is there any potential? Is there? No. So this is actually just energy. So I get PV equals 2/3 E. Or if you prefer, E equals 3 over 2 PV. That is an extremely important result. Why is that really important? Watch and listen carefully.
You got up.
Yes, it's very important. Extremely important. E is the total energy. The only way you could know the total energy is if you calculated the energy of each particle in the gas. An extremely difficult thing to do. Agreed?
Yeah.
Agreed. However, because of this formula, it means it is possible to know the total energy of every particle in the gas without measuring it individually. You can just calculate the pressure, something that's very easy to do actually, and the volume, something which is very, very, very easy to do, especially if it's in a box that you can measure. So what you've done is you have linked the sort of microscopic with the day-to-day. It's a link between the two realities. Kaboom! Alright? So, extremely important for that reason. Extremely important. It also shows that as the gas increases in pressure, do we have more or less energy? We'd have more. And if it increases in volume, we'd have more energy. So, if pressure multiplied by volume increases, we have more energy. So this actually means, what's the unit for energy? Joules. So the unit for PV is also joules as well. And we can actually prove that if you think about it.
Okay.
Just before, what did I say the unit for force was? Pressure?
Pascal.
Yeah, which is newtons per meter squared. And what's for volume?
Meters cubed.
And I'm left with
And
Newton meter, which is a
joules.
joule. Dun dun dun. So, you do not need to prove this in the exam. It's a very long proof, but you certainly must understand it, especially the consequence at the end. Okay? So, I'll give you a minute to write this down.
Could you just...
Yeah, I tell you the steps, yeah. So, the first part was we kind of looked at this, and then we looked at this, and then we went to here.
If we decrease the volume of the box, won't that increase the pressure?
Yeah, so the P and the V aren't independent. They also have a relationship. But if you could increase or decrease the volume without changing the pressure, then you'd be increasing or decreasing the energy. So, for example, if you change the gas by increasing its volume, but kept the pressure the same, then you're increasing the energy of the gas, which means that energy had to come from somewhere, which means you were putting energy into the gas. If we do the opposite, if you decrease the gas, keep the pressure the same, but decrease it, the volume, then it's losing energy. That energy had to go somewhere, so it went into you. So, for example, if you had a big container of a high pressure gas, but you were able to sort of reduce the volume of the container by letting some gas out, maybe shrinking it down, you're reducing the volume, but maybe you can keep the pressure the same. Watch.
How will you keep the pressure the same?
Yeah, watch. Imagine you had a big cylinder.
Yes.
Okay. It's at a high pressure,
Yes.
and you decrease the volume. What should happen to the pressure? It would increase.
Yes.
So you let some of the gas out.
Okay. So you're in.
So you keep the pressure constant by letting some of the gas out, but you're decreasing the volume. So according to the formula, what's happening to the energy of the gas? It's decreasing.
Yeah.
So energy is coming out, and that energy is coming out in the form of you releasing the gas, because that gas release has the effect of trying to move the cylinder
Yeah.
to the right.
Yeah. But doesn't that mean that there's a constant ratio between the pressure and the volume of the gas?
If you don't let energy in or out of the gas, if you keep energy conserved, then yes, you'd have P1 V1 equals P2 V2, and that comes from conservation of energy.
Okay, now that's the other question. It's all linking up. Doesn't that mean that each gas has its own kind of energy?
This
Kind
is
of constant for every different element or gas? You get where I'm coming from?
no, what kind of, but no. This formula says the only thing you care about for a gas in knowing its ability to store energy is its pressure and volume. What the gas is doesn't matter. Now you might object and say, that's ridiculous. But remember, we made some very specific assumptions about the gas called ideal gas law. So from the very beginning, this is only true for ideal gases, which aren't really many gases. So if you said, well, I found this gas that doesn't obey this formula, like, well, I would hope so, because this is a very particular formula for a very particular situation called an ideal gas. In real life, we don't deal with ideal gases so much, but they are good approximations. And the more accurate formula will be much more complicated than this. So it's kind of a fair balance. You have an extremely easy formula to calculate something extremely difficultly, but it's not something that you could do easily, so you're happy to sacrifice some accuracy to be able to do it easily. In physics with the formula, sometimes there's a balance between accuracy and convenience. Okay, did we write this proof down?
He's roasted.
Yeah. Yeah.
Blown out. Couldn't take it anymore.
Kaboom.
Kaboom, boom. I have 3 weekends.
I don't think there was.
I'm not coming. Spoken, but I spoke.
N?
Yeah, N particles. That should really be a big N actually, not that it matters right now for today.
N over 2?
Yeah, N over 2. So I'll give you an example of a question in an exam on this topic. I think maybe 2 years ago the question was, in the ideal gas law, or proof, no sorry that wasn't it, it was in, yeah sorry, in, this lesson was called Kinetic Theory of Gas, so this you might call the kinetic theory, this is. So in the kinetic theory, what does the pressure represent? So I'll say that again. The exam question was, in the kinetic theory, what does the pressure represent? So, if you remember the proof, you realize the pressure comes from looking at the change in momentum. The change in momentum of what? Of the particle hitting the wall and changing its direction. So you could say the answer here is, what is the cause of pressure in the kinetic theory? The cause of pressure in kinetic theory is that the change of momentum when the particles of the gas strike the surface of the container and change the direction, or something like that. What I would probably do if I was doing the question is, I would just do this much of the proof and then stop here. Well, divide by A maybe. So I found a formula for what the pressure is, but all they want is a sentence. You don't need a formula.
So, can I just say, it's caused by the collision of the
Gas particles,
with the wall?
yeah, and the change of their direction. Another type of a question that I can imagine that they didn't ask, but I can imagine them easily saying something like, in the kinetic theory, what is the interpretation of pressure by volume? So the answer is, pressure by volume is a fraction, 2/3 of the energy. Or, if you didn't remember 2/3, you could just say, pressure by volume is proportional to the energy. What other questions could they have for the exam? Let's see. Yeah, they could ask something like, what formula do you need to calculate the force? So what formula did we use here to calculate the force? Did we use MA? Delta P over delta T. Okay, so you don't need to remember how to do this, but you need to remember it and understand it well enough to answer questions about it. Okay, continue? Yes, hang on, let me just see what I wrote on the next slide.
Oh, we have 6 more slides.
Yeah, we got these, and I already talked why it's interesting. Okay, there's another proof here, which we will do, of course, in the next class. Okay, so there's not lots of proofs, but this lesson is mostly 2 important proofs.
Yeah,
You remember this proof? Out of interest, did anybody see the previous proof before?
no, the previous one, no. But this, I know I studied.
This is more common, yeah. Lee,
Viscosity.
the previous proof, did you see it before, or is it new?
Did you ever see it now?
That is a very good question. And on that note, we will finish.